Hello, hello. Let's do force on a wire with current in it in a magnetic field. Now, this is basically the same idea as the charged particle in magnetic field, but now you've got a wire full of moving charged particles. So you calculate it a little bit different, but the idea is exactly the same. So if you've got a wire, it's got current moving in it perpendicular to a magnetic field. The wire is going to be pushed in a direction perpendicular to both the wire and the direction of the magnetic field. So exactly like the other guy. Another cross product like thing. The force ends up being perpendicular to both the direction of the current and the direction of the magnetic field. And if the wire is parallel to the magnetic field, it's not pushed. So if you got current pushing current flowing in the same direction as the magnetic field, or current flowing in the opposite direction of the magnetic field, no effect. All right, so the third right-hand rule, wire version, exactly the same idea, except instead of the thumb being the direction of positive particle, it's the direction of conventional current. So everything else is the same. So thumb points in the direction of conventional current flow. Fingers are again the magnetic field. Lots of field lines, lots of fingers. And your palm has a lot of force. It's applying the force straight out of the palm. So yeah, that's about it for this guy. Thumb, conventional current flow. If you want to use your left hand, you can do electron flow. But generally you just stick with conventional current flow. Fingers magnetic field, and palm is force. Here's our lovely formula. Our force is equal to in newtons, is equal to our magnetic field strength in Teslas, times the current in amps, times the length in, what do you think? Probably meters. But of course, the magnetic field and the current need to be perpendicular. Or length, depending on how you're thinking about it. So the sine theta here just finds kind of the perpendicular component of the wire in the magnetic field. So theta is the angle between your magnetic field and the wire. So L sine theta just gives you the component of the wire perpendicular to B. Yeah, so F bill sine theta is how you do it. And notice this is exactly the same phenomenon as the force in a charged particle, just a different way of looking at it. If you do Q times V, you've got coulombs times meters per second. Whereas if you do I times L, you got coulombs per second times meters. Notice either way, you got coulomb meters per second, and then multiplied by Teslas to give you force. Yeah, I can't ask questions, unfortunately, in this format. All right, let's do some examples of the right-hand rule. So notice I've got this legend here. Red is for the wire, black is for the magnetic field. Hopefully that was obvious anyway, but if not, there you are. Red, I'm talking about wire, and my little red arrows are talking about conventional current flow, and the black is the magnetic field. So let's do this first example here. We do a right-hand rule, thumb in the direction of conventional current. So to the left, fingers are into the screen or into the page. Palm points in the direction of the force, so down. So this wire will be pushed down by the magnetic force. This guy, we can do exactly the same thing, except it'll be a little harder on our wrists. We got fingers pointing away from the screen, thumb to the left again. For conventional current flow, palm is pointing up. So this wire would be pushed up in this magnetic field. In this example, we've got a wire going into the screen. So thumb going that way, fingers going to the right in the direction of the magnetic field, palm is pointing down. Again, make sure you're using your right hand for this, unless for some reason you're doing electron flow, but strongly recommend against it. It makes more sense for direction of electron than it does for electron flow, because generally you have conventional current given to you. Yeah, so palm pointing down. So again, oh shoot, I screwed this up. Sorry, my bad. Your thumb is out of the screen, your fingers are to the right, your palm is pointing up. So this guy would have a magnetic force up. And then in this case, we've got current flow in exactly the same direction as magnetic field. So our sine theta would be 0, and we end up with no net force because our F bill sine theta is 0. We've got no perpendicular component of our magnetic field in the direction of the wire, so no force. And that's it for this topic. I'll do another little quick one next on two wires that are parallel. One creates the magnetic field, and then the other experiences a force because of it. So let's talk about that next.